Awesome. All right, welcome back, everyone. We have another guest speaker today. These are always the highlights, I think, of the week. So today we have Sanjiban Choudhury, who is an assistant professor at Cornell. And he's also a research scientist at Aurora Innovation, local. He's an alumnus of CMU, so maybe some of you either know of him or saw him when he was still around. And he leads the Portal group at Cornell to build everyday robots for everyday users. And towards this, the research really focuses on a broad range of things from imitation learning, decision-making, human-robot interaction. And these are some of the topics that Sanjiban is going to be touching on today, which are highly relevant for our class. And it's going to be really exciting to see his take on the problem, which today is very interestingly and spicily named to RL or not to RL. So I'm really looking forward to it. Sanjiban, you can take it away.
Thanks, Andrea. Hi, everyone. I hope I could be there in person, but it's good. It's always good to come back home and see CMU. As Andrea mentioned, I actually spent, I guess, 7 or 8 years at CMU, so really attached to the place. By the way, the course looks really cool. I looked at the course webpage and the list of topics, and I wanted to take the course myself. So you all are very lucky to have this course. So today I'm going to talk a little bit about robot learning and this crossroads the field is at, where we are trying to wrestle with this question of how can we RL is great and all, but it's really hard to do. It's hard to get it to work on real robots. How can we avoid doing RL and still get good policies? Let's get started. By the way, since the course is called Interactive Robotics, I hope the talk can also be interactive. So feel free to just stop me anytime and ask questions. That makes it way more fun.
Sanjiban, can you see if people raise their hands?
I think I can. Yeah, I can. Yeah, the screen in front of me.
Great. And you guys can also just shout out.
Okay, cool. Awesome. Yeah. Okay, so let's get started. So I work on sequential decision making at large, which is pretty much everywhere, not just robotics. Take language models where you're predicting a sequence of tokens to write Hamlet, or diffusion models where you're sequentially denoising images to generate cute puppies, or the robots in my lab that sequentially predict actions to cook soup here with my student QT. These are all sequential decision-making problems, and reinforcement learning is a really powerful way to think about these problems and find optimal policies. But the sad truth is RL is really hard. I mean, I'm sure many of us here have our own personal trauma of trying to get RL algorithms to work, particularly doing that at scale. Interestingly, there's been a lot of recent trends of recent approaches trying to avoid RL when possible. So if you take the domain of language models, recent works like DPO try to get rid of reward models altogether and basically go back to logistic regression. I know you're studying DPO in the next lecture. You also have things like decision transformers that basically treat RL as a self-supervised learning problem by conditioning on the recurrence. So there's definitely a lot of attraction to get rid of RL altogether and reduce it to supervised learning when possible. And the question today is, when can we do that and still find good policies? So
Sanjiban, really quickly, sometimes your audio comes in and out. It's fine, but there's moments where you're really crisp and moments where you're a little bit more muffled.
I'm gonna take off my AirPods.
Okay. Sorry for the flow interruption.
Yeah, no.
This is good.
Yeah,
this is awesome. Thank you so much.
Yeah, no, of course. Yeah, thanks. Okay, so good. So that's what we're going to talk about today, right? When can we avoid doing RL but still find a good policy? So in the spirit of Shakespeare, I'm going to tell you 2 tales. They're going to be a tale about inverse reinforcement learning, or IRL, and a tale about model-based reinforcement learning, or MBRL. But before we dive into the nitty-gritties, it's good to start with a motivation. So as Andrea mentioned, my group at Cornell, called the Portal Group, we broadly look at building everyday home robots that can work with everyday users, such as grandma, to help her do tasks around the home. And the task we started looking at is this really fun and delicious task of collaboratively cooking, right? So, broadly, the scene is you have grandma, who's played by my grad student here, Yuki, who wants to make a recipe like vegetable soup. So you have, a system here talking, you have the human here talking to the system in natural language. You have robots going and fetching condiments, and another robot maybe stirring the soup. The bunch of interesting interactions here, for instance, the human does something like takes the vegetable soup broth and pours it into the pot, and the robot has to kind of understand that the human's coming into their space, make room, and then continue on with the task. So there's a lot of interesting algorithms and engineering going on in the background, but I'll kind of focus on one tiny aspect of the problem today. Right. So what is one of the big challenges we encountered when we started working on this problem? The challenge was trying to get robots to work reliably both with and around humans. So one of the key differences between our setting and all the other home robot videos we see out there is that there's usually no human in the scene. It's just a robot doing its own thing. Now, I don't know about you all, but I don't want robots to push me out of my home. So it's important we have to get robots to be very close to humans and collaborate with them. And so, we're treating this problem as a first-class citizen and thinking hard about it. We want robots to collaborate with humans. Let's maybe look a little bit deeper underneath the hood at what that means, right? So this is another video with a different user here doing the same task of pouring vegetables into the soup. Excuse the music that's playing. But anyways, so the thing that the robot has to do is it has to be able to sort of predict when a human is likely to come into their workspace. You can see the predictions that are made by a learned model that's forecasting the human pose, is detecting the pose purely based on the image, and then forecasting where the human might go. So there's some prediction that needs to be made about how humans might move. But there's also this behavior aspect that the robot needs to learn. For example, how much distance is okay to maintain from the human, how to move legibly around the human, and so on, right? So this was a particularly simple task that we looked at, but you can imagine more and more complex tasks like handovers or collaboratively lifting things together. And that's where robots have to show their intent and understand the human's intent as well. Okay, so the broad goal when we are trying to solve this problem is that we want to learn two fundamental things. The first is the reward function. How should a robot do a task around a human? So how should the robot do it in a way that is safe, in a way that is legible, in a way that successfully solves the task? So that's one aspect of the problem. Another is our models. What will the human do if the robot were to do X? Like if the robot were to reach for an item, will the human move their hand away or so on, right? So both of these objects are really important for the robot to be able to confidently and safely collaborate with humans. Okay, so that's what we want to learn. How have we been thinking about learning these two things? So our key kind of philosophy of trying to tackle this problem is to leverage expert demonstrations. So the way we started looking at this is a two-pronged approach. The first thing we started to do as roboticists is let's go collect data of humans doing the tasks so we can learn from this data. So we have a motion capture lab in our lab, a motion capture setup in our lab. We got users, got them to wear motion capture suits, and then go collect data of different tasks around the kitchen that we might like. And these are very high quality human pose data. And there's also an increasing amount of open source human-human interaction data that we can also leverage. And the thing is, how can we leverage this large amounts of maybe not super high quality human-human interaction data in the wild, and maybe small amounts of very high quality data that we can collect to learn two things. One, how do two humans collaboratively do a task? And two, how do humans move around each other? If human one is doing X, how does human two respond? These are the two things that we would like to learn. So I'm going to pause here to see if there are any questions before we move on. Okay.
We have one
yeah.
question.
Yeah.
You go back to the previous slide.
Yeah. Oh, sorry. Here?
So I buy, like, you want to answer the question, like, how should I do a task around a human? But why does that have to be tied to rewards? Like, couldn't you just, like, pattern match without a reward function?
That's a great question. Yeah, we'll talk a little bit about that you one of the challenges one of the challenges we'll see of trying to pattern match or learn a policy directly is that you would need data for all possible input conditions to know what output you should be doing. Whereas if you're able to learn the rewards, which is what is good or bad behavior, you can then interact with the environment to figure out what the right action is in different instances. So that is why oftentimes we see that reward functions are just a more parsimonious way of summarizing what the robot should take away, rather than trying to get data for all possible input conditions. Okay. Yeah, that's a great question. Yeah, we'll talk a little bit about it in a second, about the differences between learning rewards versus policies. But yeah, let's sort of dive into this problem of learning from expert demonstrations. At this point, it might be useful to introduce some mathematical framework to formalize this problem. So I'm assuming most people in the class are familiar with a Markov decision process. An MDP is a framework that we use to formalize sequential decision making. So in an MDP, typically it's a tuple where you have states, you have actions, you have reward functions that tell you if you're at a state and take an action, how good or bad that is. And you have a transition model that says if you're at a state and you take an action, what the next likely state might be. And we're in the setting where typically the reward and the transition functions are unknown. A few other things. So our goal finally is to get a policy that's a mapping from states to distribution over actions. The goodness of a policy is the performance of that policy, J-pi. That's a cumulative reward that the policy gathers when we roll it out in the world. We are also going to think about this problem through the lens of expert demonstration. So we're going to use pi e as to denote the expert's policy. And we're going to collect demonstrations from this expert. So I'm going to use DE to denote a data set of states and actions that the expert visits. So the states here are drawn from a distribution of states that the expert policy pi e visits, and the actions are drawn from from pi invoked at those states. All right, so that's most of the math symbols that we'll be using for this lecture. Yeah, so what's our goal? So broadly, our goal is we have some expert that's giving us expert demonstrations, DE. There are two things we could do with this. The first is the field of inverse reinforcement learning, where we are going to use this expert demonstration data to learn a reward function, RSA. And then that reward function is going to be useful to come up with a good policy that the learner can execute. So that's direction one. Direction two is we can also use that expert data to help learn models. And so that's broadly the field of model-based reinforcement learning. And then we can optimize a policy in this model to come up with, we can plan on the model to come up with a good policy pi, right? So there's sort of two routes that one can take to leverage expert demonstrations to get a good policy, either IRL or MBRL, and you use one or the other based on the situation of, do I know the reward function or not, or do I know the transition function or not? And the final goal, of finding a good policy, is to bound the performance gap between how good the expert policy is and how good your learner policy is. So we want to bound J pi E minus J pi. The tighter that is, the better our learner is doing. Okay, so that's broadly our objective. Okay, questions? Cool. If not, let's keep going. So let's look at inverse reinforcement learning. So broadly, why do we need inverse reinforcement learning? So there was a question earlier about, if we have data. So let's kind of go through this slowly. So let's say we have a car on a racetrack. Let's say we have, an expert driver. You have a Formula One driver. They come in one day, they drive the car around and give you expert demonstrations, but because they're an F1 driver, they're busy, you can't afford to keep them around, so they go off, and all you have is this offline expert demonstration data. Now the question is, how do we use this expert demonstration data to get a good policy? Now, a simple idea that you might think of is, why don't we just train a policy that maps states to actions, right? So why don't we treat this as a supervised learning problem? This idea is often referred to as behavior cloning. It's incredibly attractive. It's almost the first thing you would do if you had demonstration data. But there is a problem. There is a problem with treating sequential decision-making as supervised learning, which is, as your learner, so whatever policy you train on this data, it's not going to be perfect. It's going to make a mistake. Now, what happens in a sequential decision-making setting is, once your learner starts making mistakes, the distribution of states it visits starts to diverge from the distribution of states your expert visits. And as it's going off, for example, it starts to go off the track. Now, as it starts going off the track, because your expert never went off the track, you really don't know, you don't have data of how to recover, right? And you sort of spiral out of control as your mistakes compound over time. Okay. So in case you're thinking, okay, is this a theoretical problem? Let me sort of give you. There is too much. Give me a second. The volume. Okay, sorry. Let's try that again. In case you're thinking, okay, is this a theoretical problem? So, there's a lot of work out there right now. If you're Google or your TRI, common strategy is to go collect lots of data of robots doing tasks and train a model that maps states to actions. And I think, if you have lots of money, you can go and hire engineers to give all sorts of demonstrations of what a robot should do from different recovery positions. You can train increasingly more powerful models that map states to action. So, instead of just training and simple MLP that might states to actions, you can use something like diffusion models, and you would get policies that seem to do really well. However, if you're not Google or TRI, this idea doesn't scale quite well. So every time in my lab, in different places that I've worked, we've tried to scale behavior cloning. It simply hasn't worked. If you have limited data, and especially if you don't have recovery data, you see this problem over and over again, where once the robot starts making a mistake, it doesn't know how to recover. And these mistakes compound over time, resulting in the robot kind of crashing. So this idea doesn't work if you have limited data. It doesn't work if your demonstrations are noisy. And theoretically, we have long known that offline imitation learning methods, where you're not interacting with the environment or the user, are sort of theoretically doomed, because there's always going to be a mismatch between your training and testing distribution. Okay, so hopefully that convinces you that the path forward with behavior cloning, while it may seem attractive, just isn't likely to scale easily. So this is where IRL comes in as a very attractive prospect. So the idea of IRL is, why don't we let the learner roll out different policies and plan to recover to stay close to the expert demonstrations, right? So if only we allowed the learner to interact with the environment, not with the expert, but just with the environment, then it could try out different actions and see which actions get it back on the track and stay close to the expert path, right? So you can think of IRL from a distribution matching perspective, where there is an expert distribution. There's a distribution of states that the expert visits. We want the learner to try to interact with the environments to push the distribution to match that of the expert. Okay, so that's the idea of IRL. There's a rich history of IRL working really well in robotics. So this goes back to a lot of work that came out of CMU from 2009 to 13 that showed that whether you had mobile robots, whether you had legged robots, or robots that are playing table tennis, or self-driving cars, IRL offers a very scalable way to replace the process of a human engineer sitting and tuning cost functions, and instead learning that directly from demonstration data. There's been some exciting work recently from Google Research, from my friend Matt Barnes and team, that showed where they looked at getting IRL to work in a very global scale with Google Maps data. So it's an exciting paper that I recommend checking out. So, IRL has this rich history and recent promising results as well. So, it is an attractive alternative to behavior cloning, where you're allowing your learner to interact with the environment to hopefully correct this distribution shift that can arise between training and test. Okay, so that's IRL. How do we sort of solve this IRL problem? So hopefully you're by now convinced that, okay, IRL gives us a path to learn a good policy that can come close to the expert, but what are algorithms that solve this IRL? Solve IRL, right? So mathematically, we can think of IRL as a game that is being played out between two players. one of the players is a policy player, and the other is a reward player. So the payoff of the game is the performance of your expert minus the performance of your learner. And your policy player is trying to minimize this performance gap, and your reward player is trying to maximize this performance gap, right? The idea is you want to do as well as the expert on any possible reward functions chosen from a reward function class. Okay, so how do we solve this game? There are sort of, you can solve this game in a couple different ways. There's a primal version and a dual version. I'll just show the more commonly used version, which is the dual version right now. So the idea is your reward player plays a strategy known as the way we solve these kind of min-max games is by treating it, reducing it to online learning, where you're playing a game over a sequence of iterations. At every iteration, the reward player is choosing a reward from the class of reward functions that makes the sequence of learner policies that it has seen as thus far look much worse than the expert. And the policy player is simply trying to play best response. So it's trying to do as well as possible given the current choice of reward function, right? So you can imagine the way the game is played is at the first iteration, the reward player picks the reward. The policy player computes the optimal policy given that reward. In the second iteration, the reward player picks a reward that makes the sequence of policies that it's seen up until now look much worse than the expert. So that update looks like a no regret update, where it's looking at the sequence of policies rather than just the latest policy. And you can sort of prove that if the reward player plays this no regret style update and the policy player plays this best response style update, you can in fact find the equilibria of this game, or the approximate equilibria of this game. Okay, so that's the general strategy that almost all IRL methods out there play. So this sort of suggests this meta algorithm for IRL, where you have a set of n rounds. At every round, you are updating a reward estimate, Ri, that is making the expert look much better than the sequence of learners that you've seen up until now, right? You can think of this as bump up the reward on your expert, bump it down on the learner. And then you're updating a policy pi that's doing reinforcement learning using the current reward Ri, right? And depending on the choice of your RL algorithm or the choice of how you represent the reward, you end up getting this stream of different RL algorithms like Gale or ARL or ADRL and so on. They vary by the choice of these different parameters in this meta algorithm. But almost all of these algorithms follow this template.
Sanjiban,
Yes.
does this formulation require that your RL loop finds some globally optimal or almost globally optimal solution such that the overall game is also in equilibrium? Is that one of the conditions, or is it more relaxed?
Right. So I think the condition here is it has to find an epsilon or approximately global optimal solution. So with an epsilon of the optimal policy of the current round, given the current reward Ri. I think that's the requirement to guarantee that you will reach the approximate equilibrium.
Got it. Where epsilon is some small number.
Some small number,
Okay.
right? Yeah. Yeah, and then this is going to be the key problem we'll discuss in a second. But yeah, it's essentially it's saying that your policy better do a good job of solving the RL subroutine every iteration, um, which is a lot.
Thank you.
Okay. Other questions? Yeah.
A question in the back?
Yeah, how much does the class of functions you're picking R from matter? Like, couldn't it's some like arbitrarily complex distribution, couldn't you get some like pathological case where like the policy player kind of can't win? Maybe, I don't know.
Yeah, that's a great question. So you typically want to choose the class of R to be just big enough so that it captures everything you care about, but no more bigger, right? Because you can think about it this way: if your class of R is very small, then your learner, even if your learner is finding the equilibrium, you might not be matching expert behavior in a manner you care about, right? Because your R is not sufficiently expressive. If it's too expressive, then in some sense, it's the standard machine learning problem of having too complex a model class, right? You're going to take a long, you're going to, the reward estimate, the reward player can continually keep pulling out more and more complex reward functions that the policy has to solve one by one. It'll take a very long time for you to kind of converge to an equilibrium, right? So there is, in practice, a sweet spot where you want it to be expressive enough to capture what you care about, but no more.
Specifying that reward class, like, I don't know, as a practitioner, like much easier than specifying like the reward function, or is it still also like a lot of like fine tuning of the class of reward functions?
Yeah, no, it's actually much easier as a practitioner. Like for self-driving, where you typically have a set of a class of functions you care about. For example, the smoothness of the trajectory, or how much burden you're putting on other actors in the road, how much you're violating various constraints, and so on. So the reward function class is something we've historically have hanging around. What's annoying when you're not doing IRL is manually tuning weights of different rewards to get the behavior you want. And sometimes the weights aren't even static, they're contextual, right? So that becomes an even bigger nightmare. So historically, IRL or IOC has come and kind of offered relief in having, helping humans to sort of not have to tune each of those weights. So yeah.
Oh, we have a question in the back?
Yeah, so in the formulation like of the argmax R, like it has the notation of high expert, but in real life we don't have like a expert sitting around for us to roll out. But that sort of, I mean, assuming it's sort of constantly evaluating the real function on the offline expert data set.
That's right. Yeah, that's right.
Okay. And will that have like a sort of the quality or the description of the expert data set have a lot of implications on your like?
Yeah. So for this entire lecture, let's assume that the expert is high quality, and we need to. How to deal with suboptimal experts is a very interesting question that we're working on right now, and we could maybe talk about it at the end. But yeah, for the sake of this discussion, let's assume that the expert is high quality, because ultimately the thing you care about is competing with that expert. That's the thing you care about. So we are going to assume that the expert is high quality in that sense.
I have another question. It's more of a practical question following up from one of the earlier questions, which was, okay, so in practice, if I was to run this, my RL algorithm will, in only very few conditions, actually be very good at giving me a high quality policy. So if I was playing optimally as a reward proposer, I would propose like extremely sparse rewards, right? I'm going to force the RL to essentially like choke every single time, and you get the sequence of sequence of policies that are garbage. Is this something that happens in practice for sufficiently complicated settings where RL is just very, very hard to optimize well. And the reward player is just like super easy to exploit the RL optimizer essentially.
Yeah, if you look at any practice, I mean, that's an excellent question. If you look at any practical IRL algorithm, you're doing some sort of regularization on the reward player to prevent this, right? You're either reducing the number of updates you do on the reward player, or you're doing things like gradient penalties, just something so that the reward player, the reward that's being played by the reward player isn't completely pathological, and the policy has no hope. It has to spend incredibly large amounts of time to find. Yeah, so that's definitely have to do that in practice. We'll talk about the approach we're just going to talk about is going to try to remove some of these annoying things that practitioners have to do today.
Thank you.
Yeah. Super awesome. Okay, let's keep going then. So I think we've all hinted at the challenge with IRL algorithm, but just to sort of drive it home, I like to think of RL as trying to find a needle in an exponential haystack that Andrea just mentioned. So let's take a look. And a good way to sort of visualize these problems with RL is to look at this simple but informative example of a tree MDP. So imagine you have a MDP where every state, there are two actions, go left or go right, and that takes you to a new state, and then you can go left and go right, and so on, up to some depth h, or depth t in this case, sorry. So let's say you have a tree MDP, and you are uncertain about the rewards, or you don't know the rewards ahead of time. So the reward is typically located in one of the leaf nodes, and you don't know which one. So if I were to send this off to an RL algorithm, it would have to explore this entire tree, node by node by node, and do O2 to the T work until it finally finds the leaf node with the reward, and hence computes the optimal policy, which is to always go to the right, or the left, I guess. Yeah, to the left. Okay, so reinforcement learning, at the look of it, looks hard because there's no option but for the agent to search over all possible nodes to find this reward, and hence in the worst case it'll incur this complexity of O to the T work. So the question is, how much RL do we need when we're doing IRL? So let's take a look at the IRL setting of this tree MDP. So we have a tree here. Let's assume that the expert demonstration is shown by the blue line. So the expert always takes a left. And perhaps the expert is optimizing for a reward, for the true reward in their mind, which is there's a trophy on the extreme left node that they're trying to get to. Okay, so we don't see this true reward. All we see is the expert demonstration and this tree MDP. So let's play the IRL game in this setting and see what happens. So we initialize IRL at iteration 1 with some reward R1. Now, what we often observe in IRL is that the reward player is likely to put in some spurious reward in some leaf node of the tree. That's because the expert doesn't visit this node right now, or neither the expert nor the learner visits this node. So the reward player doesn't really, see any data from this node. And so it's entirely likely that it ends up putting a spurious reward somewhere in one of these leaf nodes. Now, if we were to send this off to our RL algorithm, it's going to search the entire tree and come up with a policy that visits the spurious reward. Without a loss of generality, imagine we break ties such that the policy that the RL algorithm comes up with is not taking the leftmost branch, but instead taking the rightmost branch to visit the spurious reward. In the next iteration, the reward player is going to update the reward by first eliminating the spurious reward because that state happened to be a state that the expert didn't visit, but the learner visit. So it's going to eliminate the reward. But it's entirely likely it might put a spurious reward somewhere else, right? And so we run RL again, and it comes up with another policy that is, again, not the expert policy, but something that's visiting the spurious reward. Then the reward player updates its reward estimate. Now it's going to remove that spurious reward but put it somewhere else. And you can see where this is going. After many, many iterations of the reward player putting spurious rewards and the policy player removing it, you finally find the equilibrium, right? Okay, so we can see that there's this sort of weird whack-a-mole game going on here, where the reward player keeps putting spurious rewards. You can think of these as the moles, and the policy player is going and whacking out spurious rewards one by one. And every time it goes to whack out a spurious rewards, it's paying this expensive cost of exp of t to find the policy. And this will happen for as many iterations as possible until all the spurious rewards are eliminated. So there was a question earlier about what if my reward function landscape is very complicated? Well, that means there's a lot of moles to whack before they find equilibrium. So yeah, so and we do observe this in practice. Like the more the more complex your reward landscape, the more work the policy is doing every iteration, and the more number of iterations you have to run until it finally finds a policy that matches the expert for all possible reward functions. I'm going to pause here for any questions. All right, so this looks really bad. First of all, I mean, we just talked about how doing RL is bad, and we want to not do RL. Instead, we want to leverage this dense amount of expert demonstration data. But now we are doing RL in an inner loop. We are like doing n times RL, which is like horrible. So how did we get here? How did we go from an easy problem, which is imitation learning, and turn that into a much harder problem, reinforcement learning? And this sort of intuitively just doesn't make sense, right? And so our key idea was the following. It was to be like graduate students and be as lazy as possible. Instead of trying so hard at every iterations to compute the best response, to compute the optimal RL algorithm, just don't even try. Instead, can we have a much lower bar and simply try to do better than what the expert would do for that reward function? Okay, so that was our kind of guiding philosophy. So this was a paper we had in ICML last year called Inverse Reinforcement Learning. Without reinforcement learning, you have Gokul to thank for these spicy titles. So what is the key idea of this paper? The key idea is as follows. Typically in IRL, your inner policy player is playing best response. So it's computing the argmax jpi at every iteration. And we know that it's inescapable. This has to be OXP of t. But what if, instead of trying to find the best policy pi, we find a good enough policy, right? A policy that's within delta of what the expert would do for that reward function, right? Can we, if we take this objective at face value, can we come up with an efficient algorithm that can bound, that can give us this sort of delta bound, but not take exponential in time, not do XP work, but do poly T work? That's sort of the goal. Okay, so that's the key idea. Don't try to be optimal, just be good enough. But can we do so by being very efficient? Okay, so thankfully there exists algorithms that's been around for about 20 years of how to turn this XT algorithm into a polity algorithm. And it's using this notion of restarting or resetting your RL algorithm, not from the start state distribution, but from the expert state distribution. So I'm going to visually show you an old algorithm that does this. The algorithm is called policy search via dynamic programming, or PSDP, written by Drew Bagnell back in 2003. So let's take a look. The idea is going to be using dynamic programming, but doing so in the policy space than in the value space that you're typically used to seeing when you look at value iteration. So here's our tree MDP that we saw before. Here's our expert demonstration. We are going to do dynamic programming using, so we're going to start from the last time step. And I'm going to reset my learner from the last state that the expert visits, okay? So I'm not going to look at the expert actions. I don't care. I'm just going to look at the state that the expert visits and ask the question, what is the best action I can take in this last time step? Okay, I'm illustrating this algorithm in the RL setting. So I should probably clarify that. So imagine that I'm trying to solve an RL problem here, where there's a reward in the leftmost leaf node. I'm given expert demonstrations that I can leverage. And my goal simply is to be competitive with respect to the expert, right? Not trying to find the optimal policy, just trying to find a policy that's as good as the experts. Okay, good. So the way the algorithm proceeds is it starts the learner off in the last state that the expert visits and says, what is the best action? Now, looking at this picture, it's clear taking the left action and getting to the trophy is the best policy in the last time step. So I'll compute that, and then I'm going to lock this in. I'm not going to change this last policy. It's frozen. I'm going to go one time step back. So I'm going to go to time step t minus 2, right? So I'm going to start from that blue state and ask the question, what is the best policy I can take at this time step, t minus 2, given that my future policies are frozen, okay? So I can take a left or I can take a right, and I can see that if I take a left and I just follow my old policy, I get to the trophy. So the best policy here is to also keep taking a left, right?
Sanjiban, really quick question.
Yeah.
Are the time indices here like real time or like fake time?
Fake time.
Okay, cool. Good.
Yeah, got it. Okay.
This is like in the optimizer, like
in the
the
optimizer.
got it.
Yeah. So just to clarify, we are solving a t horizon, finite horizon MDP of t time steps, and I'm going to compute a policy that's non-stationary, right? So I'm going to compute a policy for every single time step t, and the optimizer is. I hope this is what you meant, Andrea. I wasn't super sure, but I'm going to start from the t minus 1 time step of the MDP and solve for the best policy and then keep going back in time.
Yeah. That answers my question.
Okay, so awesome. Yeah, cool. Okay, great. So then I'm going to try from t minus 2, compute the best policy there. T minus 3, compute the best policy there, assuming the future policies are fixed and so on. And notice that the amount of work I did when running this algorithm is no longer exp of t, but it's poly of t. So we can count how much work we are doing. First, we are going over t iteration. And at every t iteration, I'm only searching the best one-step action, right? And then rolling out with my future policies. So I'm doing at best t square amount of work, right? I have a outer for loop over t iteration, and inside every for loop, I'm searching the best one-step action and maybe rolling out with my future policies. So t square is roughly the amount of work I'm doing instead of 2 to the t that we were doing before. So this is a really, so just to recap, we can think of PSDP as a very lazy algorithm. So it's not going and exploring all states in the MDP. Instead, it's exploring a narrow set of states that the expert visits. And as a result, it's only taking poly t time steps compared to xt that an RL algorithm will take. Unlike an RL algorithm, which guarantees it's going to give you the optimal policy, PSDP simply gives you a guarantee of doing as well as the expert that you are using to reset your learner, right? It's not going to try to find the optimal policy. That's not what it's good at. And so, yeah.
Sorry for breaking the flow, but like 2 questions. So is this sort of assumption on the expert demonstration that sort of they all like match somehow? For example, like what they always take the relatively same time steps and they always do similar stuff in each time interval. And second question is like how does it recover from like going off of distribution?
Oh, great question. Okay, so I'm going to start with the first. So there's no assumption that they do the same things. You can imagine the expert can be a stochastic policy. It's visiting some distribution of states. So when I said I'm going to reset of the expert state, what I'm saying is I'm going to reset off of the distribution of states it visits at time step t, right? So I can we can handle stochastic experts, no problem. And the guarantees will just be with respect to that stochastic expert. So that's question 1. Question 2, which is about how does it learn recovery? So it's not going to the guarantee will only look like being competitive with respect to the expert. So so for instance, if the expert is a poor policy that isn't able to recover, then this is not going to learn recovery, right? Because it's not going to explore all the nodes to try to recover. It's just only going to be local to where the expert visits. So there's a locality in PSDP. It is not global. So it's going to at best learn local recovery, right? So it's because at every time step t, it searches over the best one-step action and then rolls out the future policy. So whatever that best one-step action guarantees, that's what you're going to get. But you're not going to get global recoverability, which is required if you're trying to find maybe the optimal policy.
Thanks.
Can you comment? Can you also comment briefly on the difference between this and the BC approaches? For example, if you have action labels and things like this.
Oh, yes, of course. Yeah, great question. Right. So so the nice thing about PSDP here is that notice we don't need action labels from the expert, right? All we're really using are the states they visit. So this is particularly useful, let's say, when we are doing human to robot transfer, where maybe we have a notion of like, let's say you have a video of a human manipulating like a cup, right? And your state is maybe the state of the object, let's say, but you don't have the action from the human demonstration video because the human and the robot are completely different embodiments. There's no way to get the action. All you have are the states. Then you can't do BC because BC requires data of states and actions, right? But you could still use methods like this that only require the state information that the expert gives to you, right? Which is pretty attractive. So that's one difference between BC and expert. There are other examples. So in our paper, we show examples where you can, because BC is sort of blindly trying to copy the actions that the expert takes, BC never sees the consequences of making a mistake, whereas PSDP here is seeing the consequence, right? Like, let's say let's say some of the future policies that it computes are good in some states but bad in other states, right? At every time step, it's choosing the best one-step action and finishing the episode with those future policies. So it actually gets to see the consequences of a mistake and learn to choose better actions that minimize the amount of mistakes that the policy would make, right? So these are sort of two major differences between PSDP versus BC. Yeah.
Thank you.
Yeah, no, great point. Thanks. Okay, this is the only proof or whatever we're going to see in this lecture, but I thought it might be useful to just, show that we are not just hand-wavily making up this algorithm. It actually has a very there is a theoretical justification for the algorithm. So the reason it works is if you write out the differences between expert policy and the learner policy using an important lemma called the performance difference lemma, that says that the differences between performances can be written down as differences between Q values, where the Q values are evaluated on states that the expert visits, and then you're rolling out the learner from those states, right? Then you can see that PSDP is in fact trying to leverage this lemma and optimize the differences in Q values on states the expert visits, right? So you end up with if, for example, the PSDP is giving you a policy that's epsilon t at every time step t, then you end up with a performance bound that looks like t square epsilon. Now, one caveat I want to be transparent about is this is, in the worst case, the same worst case bound as behavior cloning. And that's because of the localness of PSDP, right? Because PSDP is not exploring the entire tree, once you make a mistake at any of these expert states and you go off to a part of the tree where you don't know how to get back on, you are going to have compounding errors from those states. So in the worst case, PSDP is no better than BC, but in practice, we see lots and lots of advantages. One, you don't need the action labels, as I mentioned before, and two, you do see empirically a better performance because it's actually seeing the consequences of these mistakes. But in the worst case, it has the same bad performance bounds. All right, so that was PSDP. That was sort of a more conceptual algorithm to show how we could be lazy. What do we do in practice? So one of the problems with PSDP is it's computing a non-stationary policy. So one policy per time step, which is impractical if you have long horizon MDPs or infinite horizon MDPs. So in practice, you run an algorithm that looks a little bit like this. It's like your typical policy optimization algorithms, but you're making one key change. You're replacing the reset function in whenever you're doing rollouts in your favorite policy gradient algorithm, you're replacing the reset from the initial state to reset from the expert states, and that's pretty much it. So you can just run your favorite PPO or whatever, but with this reset distribution, and that's all we do in practice. So this this idea can work with a bunch of different RL algorithms as well. All right, so how is being lazy a good idea for IRL? Let's close that loop and see how much work we are doing at every iteration. So we're back to the tree MDP. To show this algorithm, I'm going to switch things up a little bit. So let's say the reward player learns this picture at iteration 1, right? So there are like two spurious rewards. One that's in the extreme, one that's off of the second left node, and one that's on the extreme right. So those are the two spurious rewards. If I were to run lazy RL with these rewards, what's going to happen? It's going to only reset of the expert states. And as a result, it's going to find that policy that takes the detour to go to the trophy off of the second node. Then the reward player is going to eliminate this trophy, but put a spurious reward somewhere else. Again, we run lazy RL. It takes poly t, but we compute a policy pi3 that goes to this trophy. Reward player removes this. And this keeps happening until all the spurious rewards off of the expert states are removed. And we converge to a policy. Notice that we only did poly t work. In each of these iterations, we are not exploring all of the nodes. We're only exploring the expert nodes. And so while we are finding the expert policy, one of the interesting things is that not all the spurious rewards are eliminated. And that makes sense. This is a fundamental trade-off with running lazy RL as an inner subroutine, is that, since your learner is not visiting all the possible states of the MDP, there could always be spurious rewards buried in some of those states. And the learner is not going to bother to visit them, and so they'll kind of remain. And we're okay with this because in practice, we are going to end up using the policy that we learned at test time, right? Rather than the reward functions. And so, but this is just one of the trade-offs to be wary of that comes with running this lazy IRL procedure. Okay, so that's lazy IRL. So we end up with this sort of algorithmic structure that shows, we're running a policy for n iterations. At every iteration, we're computing a reward. But all we did is change the RL procedure with the lazy RL procedure, and that's it. That's all we did.
Actually, Sanjiban, I have a question. So you mentioned that you don't care to use the reward function once you've optimized your policy, but the promise of learning reward functions is that I can go to a new environment, that reward is still valid, I re-optimize it, I don't have to get more demonstration data in that scene. So if my reward function has these little quirks, right, these spurious rewards, what happens? I mean, have you guys tried that out?
Yeah, no. So you don't need to interact with the expert. But if you transfer that over to a new environment, you don't need to interact with the expert, but you still would need to solve. I mean, the thing you'll execute at test time is a policy, right?
Yeah.
So you still need to solve for the policy pi. And when you're solving for the policy pi, if there are spurious rewards that policy visits, then they will be, you'll have to run the IRL process to compute that policy pi in that new environment. So if you're doing transfer across MDPs, then we would still need to optimize for a policy pi in that new MDP, and that but that optimization process for the policy pi won't be an RL algorithm, because if it's an RL algorithm, it's going to have to visit all the states again. That's not ideal. And B, it's going to go ahead and hit all these spurious rewards, and that's not ideal either. So you're still going to be running a this sort of lazy RL procedure. But I think maybe what your question is hinting at is, what if I'm going to a brand new MDP? I don't have any expert demonstrations in that MDP. There's no way I can use the reset data in that MDP.
Exactly, yeah. But I have the reward that's it's rough, right? It's not perfect, but maybe it's still worth trying to optimize. But
that's right. Yeah, I think that's a good question. We haven't ever exactly run into this issue, right? Either in all of the applications, but I think at that point of time, if you're going to run an RL, I mean, there'll be two issues. You'll have to run an RL algorithm with that reward. That's going to be expensive. And B, maybe, I mean, if the reward has deficiencies that these spurious rewards, that RL algorithm might visit that, and that's not going to be ideal as well. Don't have a great answer for that right now.
No, I'm curious. We have also another question in the back.
Yeah, so I have I guess a related question. I feel like I don't understand what you got out of putting PSDP or this lazy RL in the IRL loop over like vanilla just doing PSDP? Because it looks like you haven't gotten still your like recovery policy and you're still just sort of learning to be locally fitting the expert demonstration.
Oh, so PSDP is an RL algorithm where it's given the reward functions and it's optimizing those rewards, right? So PSDP contractually requires a reward function. But in IRL setting, you don't have a reward function, so you still have to solve for a reward function.
PSDP has the reward function and expert demonstrations.
Yeah, that's right. Yeah.
Okay. I see.
Yeah. Yeah, so this is essentially taking that PSDP and just putting an outer loop with reward on top of it.
Got it.
Just following up on that, since on the PSDP we reset like in the reset function we go to the expert states. We would like so our horizon is going to be very short. I assume like one time step. Wouldn't it be easier just to have some reward that says like calculate the difference between our current state to the expert trajectory next state, instead of learning all these reward functions? Because it's only one time step, should be reasonable.
So can you repeat the idea again? Instead of learning the reward functions, what would you replace?
Like currently in our pipeline, each iteration we first fit the reward function and then try to optimize this reward function. And but in our in the reset framework, we sort of roll out the policy like one time step in each training.
Yeah.
So would it be reasonable if we just like handcraft a reward function that says this is the distance from the
Okay.
yeah.
Understood. So yeah, so that the thing you just mentioned at the end, that I want to minimize the L2 distance. You're kind of, by doing that, specifying what you mean by good enough, right? And L2 distance is fine for many applications, but it's a horrible metric in self-driving, right? Because imagine I have a expert that's driving, that's kind of nudging around a car, right? And I have a trajectory that's a little to the left or a little to the right, both the same L2 distance. One of them is nudging into like the actor, the other one is further away. It's clear I prefer the one further away, right? And I do not prefer the one that's nudging into the actor. So L2 would be a disastrous metric to use, and in that case, and in fact, it just works horribly when we use it in the self-driving applications. And you're much that's where this notion of choosing a good basis class of reward function comes into play, because you want to match the expert on statistics you care about, like what is the distance or from other actors, or how much burden you're inducing, or what's the control effort, and so on and so forth. So yeah, I would say that if you go down that route, you want to replace the L2 function with a slightly smarter bank of features that you want to match. And then it's not just one feature, it could be a bank of features. And now the question is, which feature do I weigh by how much? Right. And then that sort of leads you down back into IRL setting, which is where we are at.
Makes sense.
Yeah, awesome. Great. Cool.
By the way, we have like 9 minutes or so.
Yes.
So yeah, I know we've been pummeling you with questions, but yeah.
No, this is great. I
going.
think we got the heart of the matter. So the next tale is just going to be super simple. But some results, like I think, yeah. So one thing I should mention, Gokul would kill me if I didn't, is that these algorithms work ridiculously well on state-of-the-art IRL methods. Way more better than we expected it to work. So it's something that that has strong empirical performance. So these are some of the harder MuJoCo examples, like Ant Maze large, and I think the lazy IRL algorithms sort of easily achieve state of the art. This is an environment where typically IRL struggles at flat lines, like the line shown here is the latest, greatest IRL algorithm. Like Gale completely flatlines. This is souped up Gale, and you can still see it's unable to kind of match the expert here. The BC line here is also a pretty I think tuned BC baseline. This is better than reported BC baselines out there. And you can see like there's a clear gap between kind of where the lazy RL algorithms ended up versus MM and BC. So that's interesting. Yeah, I'm just gonna, in the interest of time, maybe move forward to the second story, which follows a very similar similar theme. So we're just gonna just steamroll through this in a few minutes. So that's the story of model-based reinforcement learning. So in model-based reinforcement learning, you have okay. I was going to show you this video just because I love this video. This is one of the first works of robot learning working on robots. So this is Peter Abil when he's a grad student with Andrew Ing, getting these autonomous helicopters to do aerobatic maneuvers. This is what inspired me to work on helicopters when I started my MS at CMU. So what they did is they got an expert RC pilot to come in, fly around the helicopters to do this sort of all these aerobatic maneuvers, and they wanted a policy that could do this. And they kind of went about this. They took the playbook that roboticists have used for eons, which is, I'm going to first model my robot, then I'm going to throw an optimal controller on that model, and I'm going to refine my model and so on. And so what they did is, they collected this data. They used, least squares fit to learn a model of the helicopter, and then used ILQR to plan with that learned model. And that was good enough, right? You didn't need to do anything fancy to solve this problem, which is super cool. So how do we solve model-based reinforcement learning today? The way we solve it today is roughly you collect data of an expert driving around your robot. You then fit a model to that data. You then plan with that model to get a policy. You then go collect more data with your policy and then fit a model on both the expert and data from both the expert and the learner and continue. And this has sort of some theoretical grounding, which I'm going to skip. So let's just go directly to good stuff. So this is sort of the playbook for the meta algorithm for model-based reinforcement learning. You roll out a policy in the real world, aggregate data, you train a policy on both, or train a model on both your expert data and your learner data. Then you plan with this model to compute a new policy and repeat, right? And planning here is, again, doing an argmax of your performance, but this time you know your reward function. It's the model that you are unsure about. So you're sort of doing this argmax with your current estimate of the model. Okay, and the story is going to be very similar. Planning is like finding a needle in an exponential haystack. And yeah, you're hopefully planning is going to require exploring this tree over and over again. So just like we had spurious rewards with our IRL, you can imagine spurious portals in your model. Like these are shortcuts that your model learns to connect some state to some other state. So these are portals that are taking the learner from a terminal state to the goal that are incorrect. You can think of these as bugs in your simulator. And so every time you do this planning, the learner exploits one of these bugs, and then the model has to go and fix this bug and so on. And this continues. So blah, blah, blah. Okay. Whack-a-mole again, right? So every iteration, you're computing a model, you're doing XT work to solve for that model. Then the model player is whacking out that mole. And here the mole are little portals that you learn in your model that short circuit part of your state space. And this process continues. Key insight remains the same. Be lazy, don't compute plan, just do better than the expert. Different cast of people who worked on this problem. Not coordinated at all, just happened to be the same idea. I'm going to skip this math. Nobody cares. 1 second. Yeah, so the idea is, same thing, we use PSDP at every iteration, where instead of exploring all the state space, we are sort of exploring only the states that the expert visits and resetting off of that. And as a result, we end up eliminating, like learning the correct model locally around states that the expert visits, and find the optimal policy. But again, we end up with a model that might have bugs elsewhere in places that the expert does not visit. But that's okay, because what we really care about is getting a policy at the end of the day. And so, yeah, that's a model-based RL algorithm. We call it LAMPS. And all we did is go and take your favorite MBRL algorithm, replace the optimal controller there with a lazy planner, which is much more faster. And just to show you like some results, so we took the classic Abel and Ang setting and replaced the planner, which was an ILQR that had to iteratively solve the actual planning problem, and just replace it with an LQR, which is just one backward pass and you're done. We end up with an algorithm that is requires way less computational work to find a policy that is equal or even better than the policy we get by running vanilla model-based RL algorithm, which is pretty cool. And then we did it on a bunch of MuJoCo experiments where it's better, yada, yada, yada. So I just want to end by this key takeaway. So I guess we talked about two very important class of algorithms that exist today: inverse reinforcement learning and model-based reinforcement learning. And I sort of wanted to, show you the dirty laundry, that both of these algorithms today require solving reinforcement learning in a loop. And that should bother a lot of us, because imitation learning is supposed to be much more efficient than RL, right? So RL is hard. You have to do OXT work to solve an RL. And so can we avoid doing RL if we have expert demonstration data? Can we have interactive learning algorithms that avoid doing RL? And the answer is yes. You can be lazy. You reset from states that the expert visits, do polity work, and so on. And there are a bunch of open challenges we're trying to work on. I think our North Star is we really want to get, going back to the video I showed earlier, we want to get good human-robot collaboration policies by learning from human-human data. And there's still lots of challenges with embodiment or capability gap that we're dealing with. I think you'll talk about some of those in your next class, which is great. Someone mentioned suboptimal demonstrations. This is the actual real problem we deal with when we work with demonstration data. And I think while there are lots of practical ways to overcome suboptimal demonstrations, there doesn't exist good theory around it. And that's something we're working on at the moment as well. And with that, I'm done. Acknowledge all the wonderful folks whose work that I showed today. And yeah, if there are any last questions, love to take them.
Thank you, Sanjiban.